All right. Is everybody ready and excited? All right. That didn't sound very exciting, but okay. All right. So before we get started, I mentioned to you this morning that we have a series of agreements that will be signed in the next few days between ICAS and various organizations. So the very first one is actually with Clean Aviation, a joint undertaking, and Axel Krein. Axel has been with us for many, many years as a member of the panel, and now he's a member of the executive. He's obviously a very well-known individual within the European and international circles in his pioneer work, and of course with Clean Sky and Clean Aviation. So with this memorandum of agreement, we are joining forces in the years to come. In fact, the entire track that you will be part of in the next few days is to a great extent the work and help that Axel, Rachel Walls, and Paul Vigan have put together. So we're very thankful for bringing a lot of your performance and your organization behind this, Axel, and we're very honored to have you. So I will go ahead and sign on behalf of ICAS and date it on today's date. And Axel, if you want to say a few words, and off to go.
Thank you, Dimitri, and good morning to all of you. Yeah, as you all know, Clean Aviation is a European program, and if you don't know, then you will know probably after my short presentation later. But as the challenge of sustainable aviation is global, we are reaching out to global organizations like, for example, ICAS, in order to improve the way of working, the exchange of information, scientific information, technical information. And I think ICAS is a world-renowned organization with those competences. And we are very happy to exchange and formalize this exchange in a way to optimize the information flow and also to organize communication activities together. So very happy to be here and sign this document today. So,
thank you. Can I take a picture of this?
Axel, you can stay up here. Okay, so we're already eating into our first speaker's time, but you've already introduced him. I want to give you just a couple words of introduction on this track that Dimitri referred to, called the Global Sustainable Aviation Track. We had this idea a year ago, and it's amazing we've gotten to this point. We wanted to try to not have like individual country sessions, but show kind of global activities and progress towards sustainable aviation. And we're looking for kind of the big demonstrators, the big activities that are happening now that focus on CO2, non-CO2, all the environmental effects. And we pulled together amazingly 37 presentations across 11 sessions across all 4 days of this Congress. And we're really appreciative of all the speakers who committed and have shown up. I think everybody's here as far as I know. You'll see this in your app, but this is a snapshot that just shows, we have sessions across the entire 4 days. They don't all start at the same time, but that's consistent with the Congress outline. And since we're already eating into Axel's time, let me introduce Axel as the executive director of the EU joint undertaking Clean Aviation, and he'll speak.
Yeah, thank you very much, Rich. Sorting the. So what you're going to hear in the next 20 minutes, I think, so my 25 are becoming 20, is what's happening in Europe. So what's happening in Europe in terms of technology programs, and I'm going to introduce not only what Clean Aviation is doing, but I'm also trying to explore the things which are happening at French national level, at German, at Dutch national level, in order for you to get a better overview what's happening, because Europe, as probably many other continents, is complex. Many different programs are working, and we are aligning those programs more or less. So I think when you want to know what's happening, then it's important to understand that clean aviation, respectively, the programs which are happening at European/Brussels level are not the only ones. And I'm going to be highlighting only a few elements, as this presentation is considered to be an appetizer for the many other presentations which are happening just after me in the context of this track 1. But also all the other 16 tracks which are happening in parallel are containing many, many elements of technologies which are being described briefly by me in a second. And if you want to know something more about clean aviation, we are having a booth outside here. If you want to deep dive into one or the other area, please join my colleagues. They will explain to you in more detail. Before going into the technology, I think it's important to understand as well what is triggering all those technology programs. And triggering is the political and the scientific and the industrial ambition which has been formulated over the last years. And there's only an example here of the different targets which have been set by the EU, by some other countries. And I focus here on Europe, although some of you, at least the Canadians, will see that have put Canada up here. So I'm quite aware that Canada is not part of Europe. But nevertheless, that's geography. But in terms of technology development, Canada is part of Europe because with the signature of the association agreement between the European Union, European Commission and the Canadian government a couple of weeks ago, now Canadian entities, being at universities, research organizations, industry, SMEs, they can all contribute and participate and are being funded out of European programs. So Canada, in terms of the footprint, becomes European. And we are very glad that the competences are being added to the European context, and we are very much looking forward to integrate those competences into the projects. Next, what I wanted to do is highlighting again what the challenge is. And you see here the CO2 emission over time. We are today, roughly, aviation emits 900 million tons of CO2. And if nothing has been done, then you can follow the curve. We're going to end up at roughly 2,000 million tons by 2050. But the targets which have been introduced before, they are going to lead to the zero, and that's due to either technology, and I'm now on the right-hand side of the slide, either due to technology, either due to alternative fuels, either due to ATM optimization or to market-based measures, as it's called here. So technology and alternative fuels are going to be responsible for more than 3/4 of the route to target. And that's why it's so important here in this context at the ICAS Congress to speak about what are those technologies and what are the different contributions, the different elements contributing to those. This chart is coming from ATAC, the Air Transport Action Group, Waypoint 2050. There are various scenarios. This is a scenario where technology is going to be very, very important in this route to target. Speaking about CO2, you also have to immediately speak about non-CO2. And again, it's not the purpose to go into detail here. Just to make you aware, and I think most of the people are aware by now that CO2 is one element, but there is at least NOx and contrails, as you can see that here, contributing also significantly to effective radiative forcing, as you can see, and to global warming. And unfortunately, the level of confidence in how much NOx and how much the contrails are contributing is not so well developed. And this is visible in those whiskers, as they are called, going to the left and the right-hand side, those black lines there. So high confidence with CO2, that the bar is there at the right point, much, much lower confidence with NOx and contrails. And now the question is how to do trade-offs. I mean, trade-offs, you just fly around those super saturated areas, no contrails, but you add, obviously, because the distance is longer, you add fuel burn, and by that you add CO2. So latest numbers, I don't know, even 80% of contrail avoidance would lead to 6 to 8% additional CO2. So is it worthwhile doing that? Potentially, but we would need to know that contrails are responsible for so much. The same for NOx. Increasing temperature, core engine temperatures, it's very good for CO2, good for fuel burn, but it's bad for NOx. So is it worthwhile doing that? I mean, that's why I'm really asking the community to put more effort and to continue with the effort which is there, but potentially putting more effort into making those whiskers smaller and smaller and smaller so that we are getting certainty about where those red bars are. And this needs to happen quickly because those trade-offs need to happen now, and the longer it takes, the more uncertainty is in the system and the more difficult it is finally to decide which route to go. And I mentioned that just to some of the colleagues here that from 1st of January next year in Europe, the non-CO2s have to be reported by the airlines. So the regulation, which is called MRV, mandates the airlines to report about non-CO2. And then the European Commission wants to look at those reportings and within 3 years, so by the end of 27, wants to determine whether there is going to be an emission trading system fee for non-CO2s. So those non-CO2s becoming quite prominent and important. Coming to the technologies now, and the Clean Aviation Program, I put it here into the middle for a good 4 billion program. We are in full swing of delivering phase 1. And I'm going to show you some of those projects in a second. Phase 2 is going to start beginning of next year. So we have a big call in March next year for the so-called phase 2, bringing the technologies from a level 4, 5, then to a TRL6. Our target is by the end of this decade to reach TRL6 so that the aircraft which are then going to accommodate those technologies can enter into service by 2035. But there are more things happening at European level, and you can see that on the left-hand side, the CESAR program, air traffic management, optimization. You're going to see also a presentation in the course of track 1 in the course of this week. Then there are initiatives, clean hydrogen, focusing on fuel cell development, electrolyzer development in order to scale up hydrogen, battery initiatives, improving battery performances, ASEA, the Alliance for Zero Emission Aviation, looking at or assuming that all those technology developments and the final implementation at aircraft level will take place. What does it mean then? What needs to be done in order to prepare that? Assuming that all of those technologies will be ready, what needs to be done at airport, at air traffic management level, etc., etc. And EASA, and one word about EASA, I think what we all experience probably is that it takes an awful lot of time for radically new technologies to find their way into the product and into the final customer use. And we have engaged with EASA now, the European Certification Authority, to join each and every of those projects, of those technical projects, to think certification already in technology development phases. There is very little knowledge at EASA's engineering community about radically new technologies, and there is very little knowledge in the technical community, in the research community, about certification requirements and constraints. And we are bringing the two together in order to bring those technologies quicker and faster to the market. On the right-hand side, countries, technology programs, going to allude to some of those in a minute, and also regional efforts. Specifically in Europe, some of the regions have quite significant amounts of money, and they're also quite keen on spending those money in the aviation context. So we have signed a couple of agreements with those and are helping those regions to align those fundings to the clean aviation context. Coming now to clean aviation, the aircraft concepts. Those are the guiding norths, and we have 4 of those, which are guiding all the technology developments in our program. So those concepts are assessing the impact. Are the promised 20% engine performance? Are the promised 7.5% aerodynamic performance? Are the 10% structural performances? Are the system improvements all leading finally to this major target 30%? And you see here the blue bubbles for the regional aircraft as well for the medium-range aircraft, 30% improvement, CO2 improvement targets, and here it's fuel burn. And if you then use an average amount of efficiency for SAF, you can reach with those aircraft an 86% reduction in CO2. If you use power-to-liquid fuels, this 86 becomes even close to 100. For the hydrogen concept aircraft in the middle, obviously no CO2, neither if you burn hydrogen directly, nor if you power the aircraft with fuel cells, and with fuel cells even the benefit of no NOx emission. So those are the guiding norms, those are it's the insurance that we calculate all those benefits always at aircraft level in order to make sure that those benefits are going to be delivered at aircraft level. Now, examples of technology programs, and you see here the 3 examples of megawatt class fuel cell propulsion systems on the left-hand side, and I kept the project names here, Newborn, Heroes, Fame, because you may stumble over those in the coming days when you participate in other presentations here, so that you can link it to this presentation. Newborn, a combination of a PEM fuel cell with a battery, 1 megawatt, 700 kilowatt from the fuel cell, 300 from the battery, scalable to more than 3 megawatt, fuselage-based application regional aircraft. Then Herops and Fame, 2 fuel cell-based propulsion systems, pod-mounted, so not fuselage, but pod-mounted. One based on a 600 kilowatt core, as you can see here, but also scalable, obviously, for regional aircraft applications. And on the right-hand side, starting with 1 megawatt, and there the preparation of the flight test, and you see here potential flight test opportunities on an A380, which are also in preparation, which are then going to happen in our phase 2. Again, as I said before, the phase 2 going to start with a big call in March next year. So jumping quickly then to the direct burn, there we have 2 projects, Cavendish and Hydea, H2 injection and combustion technology being developed there. On the Cavendish side, we had already a big test this year on a Pearl 15 donor engine, where the hydrogen combustion was tested. They're looking here as well at dual fuse technology use, so SAF and hydrogen in the same combustion chamber. Again, I'm not an engine expert, but I'm not sure how that works, but I'm inviting you to participate in one of the sessions in the course of this week in order to understand how that can be done. On the right-hand side, also H2 combustion technology and subsystem development. Here looking also at the ultra-low NOx combustion and the impact of contrails here. On the next slide here, 4 projects, 2, the very left HIAT and the very right Amber, hybrid electric turbo powertrain architectures, 2.5 respectively 2 megawatt fuel cell applications. On the left-hand side HIAT, even agnostic whether it's fuel cell powered or battery powered. They just want to have the electricity in order to provide 80% of the propulsion system with thermal and 20% with electrical energy. On the right-hand side, the hybridization level is roughly 50%. And then 2 supporting or enabling technologies, Tema for Hera and Hecate. Tema for Hera focusing on thermal management. We have heat dissipation requirements of 1 megawatt. Today in the aircraft context, we have 50 kilowatt or so a totally different level of ambition here. And on the Hecate side, high voltage, high power application. I'm going even faster. I'm getting signals from Rich here. Propulsion solutions for short medium range. 3 projects, Heaven and Switched, based on ducted fan architectures. On the Heaven side, ultrafan based, so downscaling the technology from a 100 kilopound thrust level to a 30 kilopound thrust level, adding, as you can see here, different architecture, hybrid electric architecture, enhancing the system with a power gearbox and with a lean combustion system. On the right-hand side, the core of the work is based on work which has been performed in the context of the GTF, and as well here, the hybrid electric propulsion added. In the middle, totally new architecture, so unducted. That technology development has started already in Europe under the Clean Sky 2 program about 15 years ago. We are now hopefully finishing it up to a TR6, including flight test. And the ambition here is to go from a bypass ratio, the comparable and state-of-the-art engine of today. The LEAP has a bypass ratio of 10 roughly. This Ophelia, or RISE as the product name is, so Ophelia is the technology which is leading finally to the product, is targeting a bypass ratio of 75. So also a totally different ballpark, leading to 20% at least in terms of efficiency. Coming more to the aerodynamic side here, 3 wing projects, upwing, avatar, and hair-winged, all high aspect ratio wings, 15 in comparison to roughly 10 today. And you see here the block fuel advantages, one being pursued very much on the left-hand side than in the UK program, Wing of the Future. Going to mention that again in a minute. Highlighting fuselage technologies, one which has been delivered already or is in its very final stages of delivery. So we have developed and built an 8-meter long thermoplastic fuselage for next short medium range, 1 ton lighter. It can be visited in Hamburg, and then 2 projects which have started a couple of months ago already, Faster H2 and her fuse. And you see here the Faster H2 very much focused on the tank integration of liquid hydrogen, crashworthiness requirements being looked at. On the right-hand side, a wing for hybrid electric regional aircraft with an 8% fuel saving improvement versus ATR. So to be confirmed later on, maybe you can ask Daniel, the CTO of ATR, whether that's true. Now, coming to a few examples at country side. As I mentioned before, countries in Europe have their own technology programs. In France, a very, very important one led by DGAC under the strategic initiative CORAC, providing as well bricks to the RISE program, but also working on H2 hybrid electric architectures. Very, very complementary to what we do at Clean Aviation, but it requires, again, quite some effort to bring those efforts into alignment. This is something which we are doing because there is funding, there is competence, there is a French focus here. Only French entities can participate here, while in Clean Aviation, obviously, all European entities can participate, and even Canadian, as you have seen before. The same for Germany. They have a program as well, quite similar. Just an example here of flying technology demonstration and validation platform. They have modified the Dornier 328 platform, and they are able to perform hybrid electric system tests, hydrogen propulsion system tests, and cryogenic tests in this context. So the platform is available, is operated by DLR, and is available for tests in the German context. The UK example, Wing of Tomorrow, I mentioned that already, quite a direct link to what we are doing at Clean Aviation level, a program which has been running for decades already, focusing on new wing box structure, on system integration, but also on component manufacturing and assembly. You see here 2 specimens which have been produced and tested. On the right-hand side there, the biggest 17-meter structure has been moved to the test facility in 2023. So just giving you a glimpse on those projects, we're going to have a presentation about Wing of the Future, I think tomorrow or latest the day after tomorrow. And then on the Netherlands side, a new program, 380 million, as you can see here, strong focus on hydrogen, building a powertrain, a 2-megawatt powertrain. And finally, Norway. Before I will conclude, due to the geographical context, there are a high requirement to have public transport in the north and in the west of the country, and they are developing technologies and building their Noemi aircraft, battery electric, with first flight in 2 years from now, and EIS 2030. So just a glimpse into the different technology projects which are happening. And what I would like to highlight now is, and summarize somehow, the key importance of aircraft technology for the global sustainable aviation. I think I'm running in open doors when I speak about that with you. And by looking at those different examples, I think you get an understanding about what technology development needs to do and what technology development can do in order to make this sustainable aviation a reality. But it's not just the aircraft technology we are speaking about most of the time. I think what is also very important is the ecosystem, and you see that around the inner circle there. We need to be faster. We need to look at manufacturability, ramp up. All those questions are not just aerodynamic or structural or engine performance. We need to look at ATM optimization. These new aircrafts will have slightly different optimum flight profiles, depending a bit whether they are fuel cell powered or not. So those optimization can only happen if ATM is reacting positively to that. So those bridges need to be built. Dual fuse infrastructure, SAF and H2 at airports. How to do that one? For me, that's not so difficult, but maybe we have some time in the question round to come to that one. And then the question of ramping up SAF and hydrogen significantly, the renewable energy which is required for SAF. You need 50% more renewable energy to produce power to liquid than hydrogen. Hydrogen is much more complex at aircraft level, but can we afford this amount of additional electrical energy in order to produce all those power to liquid fuels? Because we are not eating enough French fries. We don't have enough cooking oil. These are questions on top of the funding which need to be covered as well. So I was trying to rush through it now because my 20 minutes have become already many more, and Rich have been standing here for a while. Sorry for the overrun. One question less in the last round. Thank you very much for your attention.
And so I'm the session bully, not the session moderator, but thanks, Axel. So we're going to move on to the next presentation. Before we do that, though, I do want to let people know that with only a very few exceptions, these presentations are going to be available and they're being recorded. There's some that won't be. And the question and answer, like in this session, we're going to bring the speakers up for a session after all the speakers are done to take questions across the board. So our next presentation has two speakers. Arthur Orton is from the FAA, is the manager of the Krein program and of their technology and operations division. And then Roberto Guerrero is the Assistant Deputy Secretary of the Air Force for operational efficiency, and he'll conclude this next presentation.
Great, thank you, Rich, and good morning, everyone. So I'm here to kick off the presentation on United States aircraft sustainability research and development efforts, and then I'll hand things over to Mr. Guerrero to cover his portion of the presentation, and also recognition to Dr. Rich Walls, who is really a co-author on this set of slides as well. So I'll present sort of the civil aviation research and development perspective, starting with our environmental motivations, goals, and strategy, then end up covering some of the agency activities. I'm coming from the FAA perspective, so I'll cover our projects and programs. I'll summarize the work at NASA Aeronautics and touch briefly on the role of the U.S. Department of Energy in this picture as well, before Mr. Guerrero covers the Department of Defense perspective. So the U.S. Civil Aviation Sustainability Strategy really tries to target all of the environmental impacts of aviation. So emissions, those that have a local air quality and health impact, as well as those with a broader climate impact, feeding into the atmospheric chemistry and physics, greenhouse gas emissions, CO2 emissions, of course, as well as the non-CO2 impacts of aviation. And we try to take really a life cycle perspective as we do this. You'll see in some of the coming slides, we have a lot of focus on the life cycle emissions of the energy sources we're using in aircraft, with currently a lot of investment in the sustainable aviation fuel space. Drop-in jet fuels with 50% or greater reduction in life cycle emissions compared to conventional petroleum jet fuels. And we also put a large emphasis on noise as well. Axel touched on interdependencies of different environmental impacts as you design an aircraft and an engine, and this is an important one to us as well, as we try to mitigate the impacts of noise on communities around airports particularly. So this is a national strategy. We have a set of policy and strategy documents that contain our priorities, goals, and roadmaps to those goals. At the highest level, there's a National Aeronautics Science and Technologies Priorities document that comes from the White House, and one of those priorities is the sustainability of aviation. We also have a U.S. National Transportation Decarbonization Roadmap across different modes of transport, and then specifically for aviation, we have the U.S. Aviation Climate Action Plan, which sets a goal of net zero greenhouse gas emissions from the sector by 2050. That lays out action in areas of aircraft technology, research and development and deployment, operational concept development for efficiency, as well as sustainable aviation fuels. And you'll see the sustainable aviation fuels actions are further detailed in a SAF Grand Challenge roadmap across the government, and we also have a U.S. National Clean Hydrogen roadmap and strategy. So how do we look at this? As we see the path to civil aviation sustainability, we're thinking of this as a long game in terms of it's useful to think of this in terms of eras. Of course, we have our net zero goal for greenhouse gas emissions in 2050 and need to accelerate towards that in the coming decades, while also understanding and reducing further the non-CO2 impacts of aviation. So our first era is one of evolution. We still see the persistence of tube and wing aircraft using existing infrastructure, but transitioning to drop-in sustainable aviation fuels, increasing electrification of the aircraft, and evolutionary gains in efficiency to reduce emissions and noise. This may not be the most glamorous from an R&D perspective, but it's nonetheless very important because these gains early have a compounding effect, especially given some of the historically slow rate of fleet replacement and expansion. Era 2 is one of revolution. Here looking at vehicle architecture change, propulsion system architecture change, major adoption of SAF, mild hybridization of the propulsion system, and all supported and enabled by minor infrastructure changes. So here you see an area of growing technical risk, which our R&D hopes to mitigate, but also growing impact, especially in terms of benefit. And Era 3 is one of transformation in transportation. Major vehicle architecture changes, non-drop-in fuels and energy sources, many megawatt electrification of the propulsion system, and enabled by major infrastructure changes. So we see this, of course, transformation does not happen overnight, so we're making simultaneous, deliberate, long-term investments in each of these eras of change simultaneously, and especially trying to use our government resources to enable tackling technical problems that may be beyond the risk tolerance of industry to undertake alone. So we'll talk about the roles of different agencies in those, starting with the FAA, which has kind of more of an evolutionary focus. So the chief program here is the Continuous Lower Energy Emissions and Noise, or CLEAN program, which I manage, which is the FAA's premier industry partnership to develop new technologies that reduce fuel consumption, emissions, and noise. So technologies start this program in the TRL 3 to 5 range. So they are more than just a concept. They're believed to be feasible, but they require resources to accelerate them to full-scale ground and flight demonstration, TRL 6 or 7, the goal for most projects under the program. The program started in 2010 and has been run in 5-year phases. So for each phase of the program, it's a new open competition for the industry to propose and develop these technologies against this set of goals, with the FAA putting up about $100 to $125 million matched by the industry partners. So at the end of each 5-year phase of research, the technologies have had the technical risk reduced, the benefits demonstrated, and the industry partners are in a position to take those technologies and integrate them into their next generation aircraft and engine products. So CLEAN's focus is really one of acceleration of into deployment and adoption. Here's our current phase of research. You'll see sort of the aircraft walk-around chart here, work across the propulsion system, the airframe, the aircraft systems, and sustainable aviation fuel work that's supporting particularly testing for qualification and ASTM approval of new SAF fuels. We're working with 8 industry partners right now. You'll see around the different areas of the aircraft, and each of these technology projects here is color-coded by the benefit area they target: fuel efficiency, emissions, and noise. So you'll see under CLEAN 3 quite a lot of work in the nacelle, fan, and bypass of the engine, with a focus on ultra-high bypass engines, some of which is very nicely complementary to the clean aviation work. We also have work with on that side of the Atlantic with GE on the open fan architecture for the RISE. A lot of work in the engine core across efficiency, noise, and emissions. And then on the airframe side, quite a lot of noise focus within the current clean program, quiet landing gear, quiet high lift technologies with Boeing, some electrification of aircraft systems, and some operational opportunities as well. So Clean is the sort of the premier industry partnership. This is complemented by our academic research partnerships under Ascent, the Aviation Sustainability Center of Excellence, focused on applied R&D at any TRL, tackling the same set of goals, working to advance the state of the art of knowledge across the industry more broadly with publishable results on individual technologies, but also enhanced analysis and design tools and test capabilities. And most recently, we've expanded our portfolio with the new FAST program, Fueling Aviation Sustainable Transition, with greater government-side cost share, a focus specifically on fuel efficiency and greenhouse gas emissions reduction, and unique within our portfolio of research, across a broad set of awards. This also includes some work towards electric, hybrid, and hydrogen fuel cell regional aircraft concepts. Also very important to the U.S. civil aviation sustainability strategy is sustainable aviation fuels, or SAF. The SAF Grand Challenge was launched as a multi-agency effort to work towards really ambitious goals. 3 billion gallons of U.S. domestic SAF production by 2030, and putting us on a trajectory for 35 billion gallons by 2050 for SAFs with at least a 50% reduction in life cycle greenhouse gas emissions. These various agencies came together to lay out a roadmap of 6 key action areas, and the FAA's role spans four major pieces of these. Testing, evaluating SAF performance and providing data for qualification, analysis of the environmental and economic sustainability of different fuel production pathways, coordination to enable development and deployment of SAF, both domestically and internationally through ICAO, and most recently, direct support for deployment with the new FAST grant program's SAF component, providing about $250 million for SAF production, transportation, blending, and storage infrastructure. So that's really the FAA perspective and piece of this, which in terms of those eras we talked about earlier is primarily focused on evolution and a little bit of revolution. And now we'll move into talk about NASA's efforts, which have revolutionary and transformational pieces, certainly. And sort of key in amongst this is the initiative, the Sustainable Flight National Partnership, an effort to accelerate towards that net zero greenhouse gas emission goals, reduce non-CO2 climate impacts, and apply this research for entry into service into the 2030s. So in the airliner design side, both engine and airframe focus on fuel efficiency and emissions reductions. Also the operation of the airliner in the airspace itself with a focus on integrated trajectory optimization. Enabling use of 100% SAFs, and understanding and mitigating the non-CO2 impacts of aviation. So the overall goal of the SFNP here is a next generation air transport using 30% less fuel, having both the current and the future fleet fly optimal trajectories for operational efficiencies on engines burning SAF that provide at least a 50% reduction in greenhouse gas emissions. So zooming in on the ultra-efficient airliner side of things, NASA has identified 4 priority technology areas based upon years of study of research looking at 2030's application and entry into service. On the vehicle level, aerodynamic efficiency provided by the transonic truss-based wing has the potential to provide 5 to 10% fuel efficiency benefit. Lightweight composites with a 4 to 6x manufacturing rate increase, providing weight reduction, of course, thereby fuel efficiency and emissions reduction, but also enabling new structural and aircraft concepts. A lot of work on the small core gas turbine, 5 to 10% potential energy or fuel efficiency benefit while enabling future hybrid electric engine concepts, and the electrification of aircraft propulsion itself with both fuel burn and maintenance benefits. This has also been recently supplemented with a look at propulsion airframe integration opportunities as well. So these are some of the key areas that the SFNP is bringing forward to ensure the U.S. industry is put on a new S-curve of development for the next 50 years of airliners. What you see on this slide is sort of those priority areas turned into more of a programmatic timeline focus. So you'll see the transonic truss-braced wing being developed with a planned demonstration on the Sustainable Flight Demonstrator, the X-66, awarded to Boeing to develop and demonstrate. The composite side being run by the HICAM program, the small efficient cores under the high-tech project, and then the electrification side, both under EPFD and the Advanced Air Transport Technology project. So this is really a trailer. Each of these areas will have their own presentations in this track this week for more information. But you'll see kind of the common theme here is achieving TRL-6 later this decade in time to inform industry product decision-making about those 2030 aircraft. And also throughout here, in parallel, a model-based systems analysis and engineering thread that will be working to model and virtually integrate these technologies together with a digital flight test before the end of the decade. So all of this work on the ultra-efficient airliner is then complemented by a set of operational demonstrations. NASA has a primary role in developing these new concepts to optimize flight operations and then transition that research to the FAA for implementation and the operation. So a current operational demonstration focused on pre-departure rerouting, reducing surface delay, thereby reducing fuel burn and emissions, not only for the aircraft being rerouted, but all of the aircraft operating in that environment at that time. There's 3 follow-on demos, a gate-to-gate trajectory management focus with more of an en route efficiency focus, work towards improving recovery from irregular operations, and then culminating in a capstone demo that's full 4D trajectory optimization end-to-end with data sharing and collaboration amongst airspace users. So as I mentioned, once mature, these technologies and concepts transition to the FAA for implementation. So we continue to work hand in hand throughout all this. And lastly, before I wrap up, I did want to touch on the increasing and significant work around non-CO2 impacts of aviation, including contrails. And just last year, NASA flew their DC-8 aircraft behind a Boeing 737 MAX with LEAP-1B engines to sample emissions and look at how changes in fuel composition can affect emissions and can affect contrail formation. So the lead aircraft was burning a variety of fuels over the test campaign, 100% SAF and various Jet A's, and the chase aircraft, which you can see the perspective of in the bottom left image there, was flying directly in the plume of emissions behind the lead aircraft, taking first of its kind LiDAR visualizations and measurements of the actual emissions and contrail formation. And there's actually a presentation later this week that will go into more detail on this too. And certainly there were a lot of important interagency and international collaborators that you can see some of on the screen there. So to wrap up the civil side of this presentation, I'll come back to these eras. And this slide was kind of a different version that shows some of the agency roles there on the left. So you can see FAA takes a focus primarily on evolution while supporting some of the revolutionary work. NASA's SFNP is squarely in that revolutionary space, and NASA's working beyond SFNP into the transformational space, all complemented by some of the work of the U.S. Department of Energy and their Advanced Research Projects Agency for Energy. So I guess the overall message here is it's a trailer for a lot of the presentations you'll see this week from the NASA projects, as well as from a lot of the FAA Clean collaborators. And you see we have simultaneous R&D investments across all of these eras to move us forward. So thank you. And I'll pass things over to Mr. Guerrero.
All right, green goes forward. So as a former pilot, I think I could figure that out. So hi, I'm Bert Guerrero. I was an Air Force and Navy pilot for most of my career and then transitioned to this job working in the Pentagon. Looking at operational energy, and for us, operational energy is aviation fuel. We burn on the order of $5 to $8 billion of fuel every year. We have a climate action plan that, I'm not getting any luck here. That's why. So we burn about $5 to $8 billion of fuel, depending on the price and depending on other things. And so, my job is to determine how do we continue to burn that fuel efficiently so I can spend less on operational costs, get more training, get more capability out of our aircraft. You'll see a lot of my presentation is really about legacy aircraft. Some of our aircraft have been flying for almost 100 years, and so and some of them are planned to fly over 100 years. So some of it is actually looking at the technology and applying things like computational fluid dynamics to increase aerodynamic efficiency, as well as looking at propulsion enhancements of those airframes in order to get them to be more efficient than they have been in the past. And our climate action plan, which is online, anybody could download it. My part of the climate action plan for the Air Force is to get about a 5% in the next 5 years and 7.5% increase in efficiency in our aircraft, which equates to somewhere around $250 million to $500 million worth of fuel savings every year. So that's a reduction in greenhouse gas emissions. That's a reduction in our costs. That's money. In the U.S. government, the budget is a zero-sum game, so that's more money to spend on other things as opposed to burning it out of the tailpipes of our aircraft. Not sure why I'm not having as much success with this. Okay. So just in general, our mission is to increase combat capability of our aircraft, and our vision is to create an energy-optimized Air Force. And we go after it in 5 different ways. The first one, Fuel More Fight, is really to look at the airframe, look at the system. My background prior to taking this job was in safety, so I did a lot of work in mitigating mishap through both process as well as technology. So that part is really the technology part. How do we make our aircraft more efficient by aerodynamics and propulsion enhancement? No Fuel, No Fight really for us is about understanding the ecosystem of various different types of scenarios that we have and understanding what the mitigation efforts that we have allow us to achieve more or produce more combat air power for a limited resource. In this case would be fuel. Accelerate to win. So that second part of it, really, there's technology, but the process part is a big part for us in the Air Force in that, and you'll see in my presentation, there was a time there where we were using pretty primitive tools in order to plan these very complex missions and complex series of missions of many aircraft. And we're really trying to step back into the 21st century in that case, where we're using computers and then AI, ML to actually optimize our plans. The data-informed decisions, that's another piece that we were really lagging on. Some of our aircraft, to include the F-16, which is one of our, we have almost 1,000 F-16 fighters. Not many of them, like on the order of 2%, collect in-flight data that lasts more than 15 to 30 minutes. So the majority of our in-flight data collection for those assets is 98% is 15 to 30 minutes, which helps you in mishap prevention. So you know what happened right before the mishap happened, but you really don't understand the full mission in order to optimize it. And then that last piece is, this is part of it, engage informed stakeholders. We have courses that are teaching operational energy because the fuel piece often gets ignored in the planning for scenarios that we do, but then we also learn about it much when we have a scenario that we have to actually operationally do and we don't have enough of that one resource. So really quickly, just in the legacy aircraft modification, we've been doing a lot of work on these aft body drag reduction efforts. As you can see, some of them, they pay for themselves very quickly. Printing out 3D plastic fins and putting it on the side of a C-17 will pay for itself in like 7 months. The same thing in the C-130. These aircraft that have a big upsweep in the back because of the ramp can benefit from aft body drag reduction. This work is also being done in the U.S. airlines these days, and we're seeing some pretty good results from them as well, and in teaming with them to ensure that the technology continues to get fostered. Now, there's some complications in aircraft that when you have aircraft that are designed for things like airdrop, you got to mitigate that risk that could happen to a person going out the back of an aircraft or a piece of cargo going out the back of an aircraft. So that's something to consider. What we found is that when you're doing that type of work, you also find other things like windshield wipers, and again, working with airline partners to advance these type of technologies. You also find that they discover things. For example, one of our airlines discovered that 7 out of the 10 aircraft, it performed exactly like that CFD said. They got their 1 to 1.5% on the aircraft efficiency gain. The ones that didn't, turns out that they had issues with the aircraft rigging. And they only found that by flying the aircraft a couple of years and collecting that much data, and it was obvious to them that something was different in those airplanes, which turned out to be their oldest airplanes as compared to the other airplanes. And so it's that type of learning that's going on in the airlines that we're trying to adopt as well. And then we're doing some work on just engine sustainment, just washing an engine better, coating an engine blades better. In some cases, when you reuse the blades, you have to make sure that you're reusing those, that the shape of the blades that you're reusing are optimized. So there's things there that we've had a lot of discoveries. And again, this is like maybe a 1 to 2% gain. Some of this stuff, like the aero stuff, just starting to get going on. So we won't actually have aircraft that are, flying like all of them, like all our C-17s are probably a couple of years before I start seeing those benefits. These are starting to happen right now in some of our engines. And you'll see that, that the real gains that we're getting was in mission planning, going from, whiteboard with dry rape markers and magnets for a 50 tanker, 250 aircraft schedule to something that actually gets us 3.6% better. And then the next version of that is what do you do when you do AI, ML, and have algorithms that help you optimize, and you can get 10 to 20% better just depending on the scenario. And then this is the kind of savings you start seeing. This is primarily through mission planning tools and just culture change, 70 million. And this is a cost per flying hour change. So we're seeing a pretty big impact dollar figure wise in the Air Force just by being smarter about how we execute the mission. And then this is our big idea. My office worked with the Deputy Secretary of Defense to fund this blended wing body program. We plan to fly this thing in 2027 as a demonstrator aircraft with a company called Jet Zero and Scale Composites, and you'll be hearing more about that tomorrow. There's a session on it. For us, we think there's value to this public-private partnership. We have an interest in this because this helps us deliver a lot more cargo, a lot more fuel at far distances, and we know the commercial airlines have interest in it because they can deliver passengers with about 30% less fuel. And this is just kind of a picture of what we think. At 4,000 miles off the coast of Australia, you can refuel 6 F-35s as compared to just one with our KC-46 or KC-135. So it's a big operational benefit for us. And then just finally for us, we're going to burn a lot of fuel. We know we're going to burn a lot of fuel. We're trying to find out ways. We burn more fuel in the Air Force than all the other services combined. So the Army, Navy, Marine Corps, add those all up, those are less than the U.S. Air Force. And that's why the Air Force is taking the lead for the sustainability piece, because we know it's a big dollar figure that we can take advantage of. And that's my presentation.
Okay, so our final presentation will be Guy Norris, who's a senior editor at Aviation Week. You've seen a snapshot of kind of what's going on in the U.S. and in Europe and the UK. This is going to be a look at kind of the Far East, and we really thank Guy for coming here to share his views on this.
Hi, good morning. It's still just good morning, I hope. Well, yeah, as Rich said, this presentation sort of is been put together, really, I suppose, by myself and my colleague Graham Warwick, some of you whom you may know. He's the tall, hairy one, and I'm the slightly smaller, less hairy one, just in case there's any complication there. Anyway, our goal is to basically summarize the main areas of sustainable aviation research and technology across a broad geographic region. As Rich said, obviously you've heard about Europe and North America, but what about Asia and the Asia Pacific? They're playing an increasing role, actually, in the growing push to decarbonize aviation. So our methodology was simple. We developed a sort of an arbitrary taxonomy to sort of classify the major sustainability technology initiatives underway in Europe and North America. And we divided that into 5 main themes. And then we basically looked at comparable programs underway in Australia, China, Japan, South Korea, and New Zealand. And so the categories, did you say it's green for forward? Oh yeah, sorry, here we go. Our categories really were sustainable aviation strategies, like that's the ICARE vision for sustainable aviation, the US Aviation Climate Action Plan that we were just hearing about from Arthur, or the NASA Aeronautics Strategic Plan. The second category really was sustainable R&T, research and technology programs, like the European Union's Clean Aviation Program and NASA's Sustainable Flight National Partnership. Then we kind of really just drilled down from there: government, government, industry, academia collaboration, startup ecosystems, autonomy and electrification. And we thought, you don't often you don't hear it moving the needle, particularly in terms of climate change and sustainable aviation, but we very much believe that the technology at grassroots level, particularly in electric aviation, for example, is going to be a game changer later on. So it's worth watching. And finally, regional connectivity. For example, like the UK's Future Flight Challenge. So here's what we found. So looking at China, if I'd been here 2 years ago at the Stockholm event, I wouldn't have been able to put this up. This is very recent. In terms of really China's vision of things, at a government level, in October just last year, they released the Green Aviation Manufacturing Industry Plan. And this is an outline to guide development of a more sustainable aviation industry by 2035. CAAC and the Ministries of Industry, Science and Technology and Finance have all combined to do this. And then just in June of this year, China created this joint fund for basic research on large aircraft, backed by the Ministry of Industry and Information Technology and the National Science Foundation of China. We can drill down into this a little bit more later on. And then in terms of government industry academia collaboration, COMAC just jointly established the Large Aircraft Research Institute with Northwestern Polytechnical University in Xi'an, China, as it works to sort of mature talent and spur innovation. So we're kind of beginning to see the beginning of China definitely taking a Western type approach to the way it wants to organize its research. And then regional connectivity. China's a really big player in this low-altitude economy, which means the sort of basically manufacture and operation of general aviation aircraft. But again, it sort of also involves ultimately the eVTOL generation, electric vertical takeoff and landing, development of vehicles, airports and airspace management systems, and of course the regional sector itself. And finally, startup ecosystems. Again, really drilling down here, it's electric aircraft, cargo UAVs, hydrogen aircraft. And in some ways, China is definitely is ahead of the West in many ways in this area. They've been the first to certify internally an electric-powered eVTOL, and more recently the AG-60 general aviation aircraft, and all electric. So moving on to Japan. You can tell one of my kids helped me with this presentation with all these fancy graphics, by the way. Sustainable aviation strategy. Now let's look at what Japan is doing. The Ministry of Economy, Trade and Industry, METI, has this new commercial aircraft plan. In terms of sustainable R&T, the NEDO, the New Energy and Industrial Technology Development Organization, has a hydrogen aircraft development program. In government, industry, academia, we've got JAXA, of course, and its well-known programs. I'll go a bit more into those in a second. Regional connectivity, again, a big focus, a lot of work on drones, UAVs for rural and remote communities. And finally, eVTOLs and drones, again, in the startup ecosystem. So moving on to Korea, let's see, we've got here again a sustainable aviation strategy. And you'll notice, by the way, as we move from China and Japan, Korea and onwards is progressively less and less of a sort of tiered evolution. I think obviously you could sort of say China and Japan are more equated to what's going on in Europe and North America, whereas when you get to the other Asia-Pacific areas, it's much more focused on particular sectors like regional development. So just picking up, there we are with Korea. There is an established Korea Aerospace Agency, CASA. This is really equivalent of NASA, but it's very much focused on space at the moment. We don't yet know really what their intents are in terms of aeronautics. Sustainable R&T, the Korea Aerospace Research Institute, or KARI, has a Future Vision 2050, which again is a very high-level sort of targeting of sustainable aviation. I think what we're seeing much more of in Korea is this focus on academia and industry collaboration, on electrification, batteries and fuel cells. But where Korea really stands out is the grand challenge that they have in the unmanned aerial vehicle area, certainly on the on urban air mobility area, which with their grand challenge. And again, a very busy, active scene with eVTOLs and drones. So let's see, if you moving down under to Australia, essentially we're looking there at the emerging EATP, the Emerging Aviation Technology Partnership. That's probably the biggest in terms of a government level program. A government, industry, academia collaboration in the Advanced Air Mobility Cooperative Research Centre. And startup ecosystem really is focused on long-range hydrogen drones and eVTOL. You can see here already we're beginning to see this sort of the way that you're sort of more of a focus emerging on a regional needs type of basis. And then finally to New Zealand. New Zealand is quite interesting. It basically, the national airline, Air New Zealand, is almost a de facto leading a lot of the national programs down there. It's intimately involved in the country's Sustainability Technology Challenge and taking basically a lead in the SAF and green hydrogen studies down there. There's also a big focus in the area of electrification, of course. New Zealand has this Mission Next Gen aircraft, and startup ecosystem, again, it's looking at airspace integration, a trial program, and that's been going on for a few years now. So we'll take a bit of a deeper dive into some of this. I think we'll start with, obviously, go back to China, the Green Aviation Manufacturing Industry Plan. It's an outline to guide development, as I say, of this more sustainable industry by 2035. The government states there is a rare and historic opportunity to apply the technologies and supply base developed by China's EV and electric vehicle industry to green aviation. So they basically established this Green Aviation Technology Innovation Center and a consortium to create a new energy storage manufacturing industry innovation center to sort of accelerate the development of key common technologies for green aircraft. It's pretty broad-ranging. They've got electric propulsion for smaller aircraft, sustainable aviation fuels, new aerodynamic configurations, hybrid power for medium and large aircraft, so that includes hydrogen and liquefied natural gas fuels. They've also got this green aviation technology innovation project called Green Plus, which focuses on sort of reducing the weight and drag and increasing the lift of existing domestic aircraft to improve efficiency and encouraging the demonstration of small eVTOLs and drones. There's basically, as you can quite clearly see, there's the beginning of a lot of parallel tracks here which strongly reflect, for example, the clean aviation or NASA FAA efforts in North America. China also plans to develop technologies for liquid hydrogen storage, low-emission hydrogen combustion, precision control, and thermal management. It's also got a lot of ground infrastructure research, particularly focused on hydrogen and transportation. And it also wants to develop a hydrogen energy system demonstration platform. So a huge amount really going on, actually. And all of it incredibly recent, too. So looking at this joint fund for basic research on large aircraft, this is basically on top of a roughly $66 billion equivalent, which was provided by the PRC state to support COMAC. That was by 2020 alone. Analysts in China estimate that the new fund will be at least several billion yuan to basically a billion yuan fund, which would be about the same as about 700 million US. And they basically are saying we want to lay a solid foundation for the long-term development of the large aircraft industry. And what's almost certainly related is COMAC has jointly established this Large Aircraft Research Institute with NPU, as we mentioned earlier. And what it really wants to do is drill down to a new path of organized scientific research and innovation. And I think you should look at this in context of history, because obviously China's evolution has very much followed, in the Cold War days. It was a lot of relationships with the former Soviet Union, and more latterly with the Western nations. But now it really wants to focus on developing its own grassroots capability. For example, the NPU facility in Shanxi province, they have the ARJ. It's the alma mater really of the ARJ-21 chief designer Chen Yong, the C929 chief designer Chen Jingchun, the 929-600 chief designer Zhao Junling. So you can see it's very much it's a center of excellence type of focus. So drilling down a bit, regional connectivity. China's moving aggressively to build on a thriving sort of lithium battery and electric vehicle supply base and bring a lot of electric propulsion to aviation. And this is just a couple of examples, as I mentioned. This the one on the top there, that's the CE-25A, a 19-seater all-electric regional aircraft, which was displayed for the first time just in November last year. And at the lower one here is the RX-4HE, which is the first hydrogen-powered four-seater under test in Shenyang. So, I'd say it's sort of an awful lot already going on. So moving to Japan, obviously the Ministry of Economy, Trade and Industry outlined plans as recently as March to launch a new program with a team of Japanese aerospace companies that would see a hydrogen-powered aircraft rolled out by 2035. It builds on the technology base established with the MHI space jet, which was sadly abandoned last year, but I think Japan wants to try and build on what it managed to achieve really over the almost a decade-long work. They don't want to waste that. And when you look at other areas of the program, they want to focus on hydrogen-capable low-NOx combustors, lightweight liquid hydrogen tanks, and airframe structures. A new public-private partnership is investing 33 billion US or 5 trillion yen into this latest program, which will be primarily focused or financed, I should say, by the Japanese Green Transformation Sovereign Climate Bond. The themes that have been meanwhile selected by NEDO, that's the New Energy and Industrial Technology Development Organization. This is part of a 10-year program, again, almost $18 billion, Green Innovation Fund. The 4 projects really are focused on hydrogen electric propulsion, core technologies for hydrogen fuel cells, integration of power control and thermal air management, and they also support the increased electrification of aircraft. There's more details in the paper on this. So meanwhile, JAXA, of course, has got a longer standing. It's a bit like sort of NASA in that respect, a longer standing tradition of this research. It's been looking into hydrogen-powered aircraft, advanced propulsion under the Sky Green Plus R&T program. And it has an emissions-free aircraft Sky Frontier project, which targets increased propulsive efficiency through, well, our good old friend blended wing body, essentially distributed turboelectric propulsion, as well as improved aerodynamic efficiency through boundary layer ingestion. JAXA and KHI have launched a 10-year research project to study core technologies for hydrogen-powered aircraft. This three-pronged project covers hydrogen combustion, liquid hydrogen storage tanks, airframe structures for the hydrogen-powered aircraft. And again, there's several more examples which are in the paper. So moving to the next one, Korea. As I mentioned earlier, the KUM Korea Urban Air Mobility Grand Challenge is the big focus really there, hosted by the Korean Ministry of Land, Infrastructure and Transports. It's one of the most aggressive government-backed initiatives underway anywhere, as far as we can see, to commercialize UAM. And the Hyundai-led KUM-1 team has already conducted end-to-end UAM demonstrations at a rural test site in Korea using an uncrewed eVTOL. And so, much more to see in this area. And let's see, moving on to Australia. Again, we're sort of seeing this latest phase of the EATP. There's been 12 projects that are sharing a $13.5 million Australian dollar contract in federal funds. That's the second round they've gone into now. And projects include sort of use of drones for large-scale farm spraying, humanitarian disaster recovery operations, and the delivery of cargo and medical products. There's a company called AMSL Aero has also received funding for flight testing and regional demonstration of its Vertilla eVTOL. And that will develop and demonstrate a hydrogen refueling system to enable regional range. So again, it's not on the grand scale that you see in some countries and continents, but it's very, very focused on particular breakthrough areas, and therefore it's definitely worth keeping an eye on. So finally, moving to New Zealand, we mentioned Air New Zealand as sort of the flag bearer, literally, of kind of a lot of the initiatives down there. They've just ordered the Alia electric aircraft from the US startup Beta Technologies for commercial demonstration flights, which are planned in 2026. It's going to be a CTOL, conventional takeoff and landing aircraft, and it's the first to be ordered under their Mission Next Gen program, and it follows a pretty intensive 18-month evaluation. Air New Zealand's also working with Cranfield on various solutions, such as the hydrogen electric Britten Norman Islander, and Aviation on the battery electric Alice, and the Volt Aero on the hybrid electric Casio 330. I think the last really area to mention is the trials program there. The government and industry partners, led by Wisk Aero, which is a Boeing company, have just recently announced successful completion of a series of unmanned flight trials in New Zealand as part of an effort to sort of demonstrate that you can basically integrate safely uncrewed aircraft into controlled airspace. The flight trials were organised as part of this airspace integration trial program. I'm not sure whether it's trial or trail, but anyway, either way, it's AITP. And so that's completely underway, and it's real. So, and then there we go. That's the hairy one. Graham, just saying thank you. Thanks very much.
Okay, thanks, Guy. So we're going to have a couple additional chairs put up here, and we have about 20, 25 minutes for questions. It's a pretty bright light up here. So hopefully there's somebody running around with microphones as well. I know I see the first question in Jim over here. But let's get the chair set up. Yeah. Pick your favorite spot. And you don't have a microphone, do you? Yeah. So you may need to. I'll stay here. So do we have a microphone in the audience? Aren't we supposed to have a staff person with microphones? Okay, there we go. I see the first question over here. Thank you, guys.
First, thanks for 3 great presentations about all these efforts. The question that came to my mind when listening to this, especially from the U.S. perspective, how much does the inertia of the U.S. industry play into the decisions and these initiatives to promote change? We have one major manufacturer who's also the awardee for the Sustainable Flight Demonstrator. How are they going to be pushed to be revolutionary and transformational?
Well, I think there's the sort of the pull from the industry side and the push from the government side, and Rich, feel free to supplement here because you are the NASA co-author on all that, right? But I think across, especially as I was talking about the NASA sort of key technology priority areas under SFD, those were really developed through a lot of careful analysis and study. So there's priorities being selected through the government research and study, and then the industry responding to those. At the same time, there's things that, for example, the way the FAA approaches the CLEAN program is we set our goals and say these are our priorities within the fuel burn, emissions, and noise, and let industry sort of tell us what their top candidates are. So we kind of, I think it's a little bit of both ways. There's sort of the pull from the industry that sets some of that, and the push from the government studies that sets priorities as well. But Rich, do you want to add on to that at all?
I just add to that. I think everybody I see in industry is highly motivated, and it shows up in the cost share. The industry is not just looking for government money to do what government wants us to do. Everybody's motivated, and they're looking to kind of skip beyond what the next kind of evolutionary step would be if they can. So there's a lot of motivation, and it comes from climate, it comes from economics, it comes from competitiveness. I don't know if anybody else wants to speak to that.
I'll just say that you saw the Department of Defense, and in particular the United States Air Force, take the lead on a couple of public-private partnership initiatives. The first one would be Agility Prime with urban air mobility, and us making a pretty significant investment in that space because we want to see what it gives us, as well as, there has to be a public interest into it in the commercial world as well to expand that. And that's really what took us to the next step, which was PWB. For us, the majority of the fuel we burn is not in vertical lift. It's in big aircraft that fly long distances, and therefore we wanted to have a similar type of competition where we put out a requirement to get 30% more efficient than a KC-46 or a 767 type aircraft in order to see who could bring us a technology, and then we're not going to pay for the whole thing. As a matter of fact, we're going to maybe pay for a third of it, but we think we can benefit from it, and we also think it'll energize the big players, because Jet Zero is a startup. It'll energize the big players to start thinking about this as well and seeing how we could create that competition to enhance the overall performance of aircraft from an aerodynamics perspective.
Maybe to build on that, I mean, government funding and the 1.7 billion we are receiving from the European Commission is obviously an incentive to go faster. But looking at it from a different perspective, it was encouraging to see what's happening in the world, not just in the US and Europe, but also in the eastern part of the world. But what I'm very much concerned about is that we are not fast enough. At the moment, as we all know, aviation is 2.5, 2.8, 3% of global warming. If you add non-CO2s, it's a bit more. Question is how much. But as I see the strong drive with all other industries decarbonizing so quickly, and solutions are in many of those industries available. When you look at the cars, I mean, there seems to be a hiccup currently with regard to electrical vehicles, but there is a technical solution available. And if those batteries are shifting performance by another 20% or so, we will get the range, and this range anxiety is going to go away, and there is a solution. And our aviation percentage, being it 3 or 4 or 5 or whatever the percentage is going to become 15, 20, 25%. And I'm very much concerned that we are not going to be fast enough, that all those other industries where it might be easier will be faster than us, and we will get a percentage which is unsustainable. And then the regulation will come in, and that's our children will vote for that. Nobody will allow aviation to become 25 or 30 or even more percent. So then there will be a regulation. I was just speaking about it before. Then I will get 1 ticket per year to go somewhere. And then I have the decision to be taken, do I visit Laura, my daughter, or Lucas, my son? And this is something where we need to be faster. We need to get those products into the market as fast as even possible. So not thinking only about the technology itself, the performance, but also how do we get it into the market faster?
We'll let everybody have a turn at this one.
Yeah, sorry. And from I know from the China perspective, the market it's much more market-driven. Obviously they do have this sort of overarching need to match the sustainability targets that are going on elsewhere. But China desperately needs to build up its own indigenous commercial industry, and it knows that the sort of grassroots research and development work that has to be it really has to catch up on the last 40 years of development elsewhere to be able to build a whole family of products, and it knows that it can't sell these products outside of China unless they meet international requirements, and that part of that is going to be sustainable performance. So, yeah.
Okay. I saw Susan here, and then Carlos, but let's go. Raise your hand, Susan. And when you ask a question, state your name and your organization as well. Our next question is going to be over here after Susan.
Okay, thank you. Susan Ying from Ampere, and formerly Boeing. So great presentations by all four, sorry. And Axel mentioned, and also Guy mentioned, we got to move fast. And also we have identified that, aerospace products are different from the EVs, for example, on the ground. Elon Musk, they can just shove in these new software updates like overnight. My cars have software updates like every other night. While as with airplanes, you can't do that. Why? Because the certifications just won't allow you to do it. So how do we get those radical technologies into the airplanes or into the products fast? We need that. And for example, FAA has worked with, we work with FAA on our certifications, and also in EASA in Europe. But like in China, we've already certified two eVTOL products, while there's none in the rest of the world, which probably started earlier than in China. Why is that? Why can't the FAAs, the EASAs, the CAACs work together to help speed up this process?
Yeah, thank you, Susan, for that question. I think that was somehow when we started the thinking about clean aviation and doing it differently in comparison to the previous program, Clean Sky, we immediately came to the point we need to onboard the certification authorities. It was very, very difficult, I can tell you. I don't know whether someone from EASA is in the room, but it was not so obvious because they were indicating, no, please, you technology guys work on technology, and then when technology is ready, you give it to the development people, and the development people we know to talk to. So they will be then talking to us and will explain us what they want to do, and then 10 years later, you have the EAS. But when we were trying to convince them that they need to be part of that process right from the beginning, to learn as well about technology development, it was quite a hurdle to overcome. It's a question of resources, a question of mindset, willingness, and you name it. But I think that's the only way forward. And I think we have not succeeded yet, but at least we have EASA engineers in each and every of those projects, and that makes a big difference. We see already that technology people who are part of the same company where certification requirements have been discussed for decades, but they have never been part of that type of discussion, because that's the development people, and it's a totally different species of people. And I think that's something where I see already the benefit coming, and I think that's where we need to push even more, that the certification authorities need to be there right from the beginning to learn, to understand, and to train the technology people to take certification requirements into account. So I think we are starting only on that journey, but that needs to be accelerated and very quickly.
Arthur?
Yeah, certainly agree with that. And FAA is a very big organization. It's 40,000 of us, and many people think of the air traffic controllers or the aircraft certification types. And I come from an office of 50 that's focused on the environment and driving a large research budget. But we've worked really hard within the CLEAN program to try to bring our aircraft certification and engine certification folks into these research reviews. We actually even have stated in our goals that part of acceleration is the mission of the program. So that's the speed theme, right? But bringing the aircraft and engine cert folks into the R&D technical reviews, and the stated goal of the program is to advance technology to a mature but also certifiable state that can benefit these goals. So we're making an effort to bring our cert folks into our research reviews, and this is also, I think, happening across the U.S. government too. For example, there's a large sort of review panel for some of the major NASA programs coming up, and we have aircraft certification folks from the FAA, even in fact chairing one of those reviews, for example. And that said, the aircraft certification side of the FAA has a number of working groups with EASA on the sort of different emerging technology spaces, and coordinating to make sure that safety is the top priority, of course, for both certification organizations, but that we're syncing up on best practices, requirements, and also making sure that the industry can move forward. So.
Just really quickly, the Air Force identified a few years back that we needed to, and this was the Chief of Staff, who is now the Joint Chief of Staff Chairman, C.Q. Brown. He wrote a paper, and it was called Accelerate, Change, or Lose, that he had recognized, and the paper pretty outlines it very well about the challenges with bureaucracy, the challenges with incentives that are provided to folks who are developing and certifying new military aircraft for use, and that we had a very dynamic and quick ability to produce new aircraft at a pace back in the 60s and 70s, really in the 60s, that we've lost now. And part of that Accelerate, Change, or Lose for us is called Accelerate, Test, or Lose. We're trying to understand the incentives by which a government employee can go quicker and use new 21st century tools to help with that certification process that they may not have been versed on in the past. That's resulted in us taking so long to produce an aircraft now than it did decades beforehand.
Maybe just one additional word. We're speaking about technology development at industry level, but also the time we need to bring technology from a university context into the industry context, or via the research and technology organizations into the industry context, is awfully long. And I think there's also a lot of work to be done to connect those much, much better than what we have today. That the technology work which is actually happening at uni level finds a faster route into the programs, going via tier 0, first thinking, to 1, 2, 3, 4, 5, 6. We can't afford that anymore. Although we can't afford to lose the safety and the security which comes with that long process and the development afterwards. So we need to find ways of working more hand in hand and connecting the people much better than what we do today.
Sorry, one last word on China as well. You mentioned how China's been really upfront in certifying, pioneering really in a lot of the ways, so like the EHang, for example, the eVTOLs. And I think that's sort of inspiring, really, in a way. They've managed to, certify well in advance of other Western nations some of these innovative advances, like, for example, the hydrogen four-seater. But of course, that's internal to China. It's a huge internal market in its own right. But the big question is, how do you then expand that out internationally, and how do you work across borders? So I think somehow that's got to be, you've got to sort of take lessons from what China's done and then bring it in to sort of include the US and Europe, somehow.
So I think we have a common theme of accelerate, accelerate, no compromise to safety, you still have to certify. Carlos.
All right, thank you, Rich. Carlos Sasnick, University of Michigan, US. First of all, thank you all for the presentations. Were really great. Before I ask really more clarification, I'll say those are great challenges. I think we're all committed to support that. That's from the academic point of view, Axel. We had this Airbus Michigan Collaborative Center that showed a way that we can do this kind of fast transition of very fundamental low TRL and move into higher TRL. I think if we can get more of these industry academia collaborations, we can really speed up this process instead of doing this in sequence. But with that said, a question actually for both Axel and Guy, primarily in your perspective of projects, it looks a lot of short and mid-range airframes and developments for such. And I missed the fact that what happens with the long range? The Air Force has this problem, right? You burn half of the total emissions or the fuel on the long range flights. What are the specific projects and technologies? And maybe I just missed that. That's why it's a clarification. And then on Guy's side, great overview there. A big looks missing place is India. How do you choose the places to investigate or to report back? And maybe why such a...
I think we gave him the Far East as the scope. And we
okay,
didn't,
so maybe it doesn't go that far and you cover that side. That's okay. Thank you.
Yeah, thanks for the question. Actually, on India, I was supposed to include a map which specifically showed the region. We're excluding India because we thought that would have deserved another one in its own right, in a way, to be honest. So apologies for not being able to include that.
Yeah, maybe to your first part, in terms of why regional and short medium range and not long range. Definitely, when you look at it, when we made the decision to concentrate in clean aviation on regional and short medium range, which is 50 or 55% of the emissions. So we left out intentionally the 45% because just for practical reasons, we have 4 billion euros available and we couldn't do everything. So we said, okay, instead of doing everything a little bit and doing nothing really, then rather focus on one, either the shorter range market or the longer range market, and we decided for the shorter range because that's more urgent, we thought, as the likelihood of products entering into the market in the mid-next decade are much higher than for a new long range where the products have been out or are about to get out into the market only very soon. But and I think that's definitely something where we have been lobbying the European Commission, because that's the public funding part we are receiving there, definitely needs to step up its ambition for the coming years. And we are starting to work already on the next framework program where definitely we need to invest in long-range research. And I know that a lot of things are going on at university, at research organization level, but that needs to be reinforced so that options are becoming available for that more long-range market. And I strongly advocate the Commission to spend money on those elements, and I do hope, because the first signals are rather positive, that that's going to happen and that we are going to see more effort on the long-range side coming up in the next framework program, which, by the way, in terms of money spending, is only 2028. So it's quite far out there, but let's make sure that the transition can happen, that the work which is being performed at the moment at university, at RTO level, is being pursued and is being supported as much as possible, and that the higher level fundings are coming then as soon as becoming available.
All right, we have about 5 minutes left, and I see a question back there, and then one here and one here. So we're going to try to do 3 questions in 5 minutes.
Jonathan Couldrick from the Australian National University. This is a jurisdictional question, but each country, region, for example, Europe, Canada, the US, are looking to reach net zero by 2050. My question is, will you assess that on a geographical basis, regardless of who flies, or will you assess that on a state level, regardless of where they fly? For example, the US Air Force, will it be judged by itself, regardless of where it flies in the world, or will Europe judge the US Air Force in Europe?
So, boy, I can't really say that the U.S. Air Force is going to be net zero by 2050, and we will look at all of our operations because it varies from year to year. So it won't be a specific, as we look at how we optimize, our part of the aviation portfolio, it'll be, the worldwide impact and what we were beforehand as to what we're able to do now.
And I'm trying to remember the fine print of our U.S. Aviation Climate Action Plan goal. It's really the scope of what we can control within the U.S. aviation sector. But I do remember that includes U.S. carriers, wherever they operate. But I also wanted to come back to, there was a large sort of coordination effort through ICAO's Committee on Aviation Environmental Protection a few years ago to study the feasibility of and come to consensus on a long-term aspirational goal for CO2 emissions from international aviation, or the LTAG, and that was set at net zero for 2050 as well. So that's anything international aviation, so that global connectivity between countries for aircraft wherever they are operating to or from. There is a goal around that is more larger and bigger than any one country's goals too.
I think you had a question here. It was you. You still have a question? Okay. Raise your hand, and he'll bring you the microphone. Oh.
Okay.
Go ahead.
Okay. I'm Peter Cruz from Linköping University. First, I would like to say this was an amazing session, and it's so inspiring to see all these technologies up in the air now. And I would say for the young people here, this is a great era to be active in research and development of aeronautics. However, there is one technology that you kind of have high hopes for, but that is outside our control, and that is the SAF. I'm very nervous about that, really. What do you think about the CO2 reduction of SAF will bring in 2050 in %?
Well, as you can see from some of my charts, from the U.S. civil perspective, we're being very aggressive on that and aspirational with our goals. We've done a lot of studies on the sort of techno-economic feasibility of different fuel production pathways, the full life cycle there from a emissions and sustainability perspective. And then as I said, we try to help support some of the testing to generate the data for safe qualification and coordinate the resources across the U.S. government and the emerging industry. But where we're, to hit those production targets and scale up to meet those kind of emissions reductions that SAF needs to deliver to hit our net zero 2050 goal, that's where we've stepped into the deployment as well, directly funding through the new FAST program, production, transportation, blending facilities. It's a step in the right direction, but there's still a big challenge to go there. So we acknowledge the challenge, but we're trying to put our resources forward best we can to help deliver on those goals.
Let's try to get one more question in here, and maybe one more.
Okay, so my name is Rafik Fir. I'm from Israel, and my question, I think, is more relevant to the US right now. There's a big focus on the aviation, but what about the space launch? As we are near in the future when we are about to push lots of objects into space, what about space launch? Are there any goals, key technologies?
Sure. Well, there's a portion of the FAA, the Office of Commercial Space Transportation, that's responsible for licensing launches in the U.S. from a safety perspective. And I know there's certainly been environmental studies about the development or approval of new launch sites that's coordinated closely with my office as well. So I'd say that's an area of sort of emerging study where we do acknowledge some of the environmental impacts of the growing commercial space industry, but a lot more to come there. I'd say no conclusions yet.
All right, I'm going to take one last one here. We're right at our deadline, but...
Okay, thank you. Rick Parker, Chairman of the Singapore Aerospace Program. Mainly for Guy, you obviously focused on the big boys in the region, but most countries in the region have a significant aerospace program. Malaysia, for instance, has its MIAB 2030, has a goal of securing $12 billion a year, US dollars a year, of aerospace manufacturing in Singapore, in Malaysia. Singapore similarly wants to maintain its world MRO at 10% of all the world's aircraft MRO and continue to grow that. Those both have to be done sustainably if they're going to be qualified suppliers to the West. And secondly, the emergence of drones and eVTOL definitely lowers the barriers to entry. Most people at least believe they can get into those markets. So I don't know whether you see any of these other countries in the region coming up fast on the rails.
Yeah, thanks, Rick. And I do apologize for, again, not including Singapore and Malaysia, but there was literally just not enough bandwidth really available unfortunately, but you're right. And to your second point about the eVTOL sort of lower barrier to entry, I honestly do think that we've seen that a lot now, that all of these countries that are not able to fund huge, great sort of R&T efforts are looking to that as a sort of a grassroots entry-level way of getting in. And I think the rest of the industry is going to benefit from that eventually, particularly with battery and hybrid electric technology, because this is where the real important research is being done. That's going to make life easier for the rest of us later on, I think. But yeah, to your point, sorry.
Okay, with that, I think we've passed our time. I hate cutting off discussion, but lunch has already been served. There's a keynote at 1:30, and our second session in this track will be at 2:30. And let's give a round of applause to our presenters for setting the stage. Much of what you saw here, you'll see deeper dives later in the track. Thank you very much.